Good afternoon, ladies and gentlemen. I hope you're all well and keeping safe during these turbulent times. My name is Andrew Spowage, and I'm a reader at Queen Mary, University of London. I'm very excited to present our team's work, and I am grateful that you have taken the time from your busy schedules to join us today. The project work was completed mainly by three current and former students of Queen Mary, University of London. The team members are Andrew McPanam, Awis Youssef, and Gabriel Santander. And I'd like to thank them all for their valuable contribution to this work. I would also like to thank the CO Research Trust, who generously funded and supported this initial study. The primary aim of the work is to gain an understanding of the current position related to CO poisoning within the UK's General Aviation fleet, and to investigate potential areas of future work that could further reduce the risks of CO-related poisoning incidents in general aviation in the future. The basic outline of my presentation is shown in this slide. I understand that our audience is mixed today. We have people who are experts in carbon monoxide poisoning, medical professionals, experienced pilots, regulators, researchers, and other interested stakeholders. I will therefore keep the presentation at a high level and cover areas of general interest without getting into too much detail. The detail, of course, can be found in the accompanying white paper. Let us start by looking at carbon monoxide poisoning within the general aviation fleet and give a little context to the study. Any fatality is, of course, a tragedy. Our level of understanding and our ability to mitigate carbon monoxide related risks has greatly improved over the years. However, incidents of CO poisoning still occur each year in domestic, commercial, aviation, and other environments. The aviation sector, which includes all flying operations, accounts for a small but significant percentage of deaths associated with carbon monoxide related incidents. That is to say, the focus of our work accounts for a small piece of a relatively small pie when it is weighed against other issues we face today, such as COVID. Let us have a quick look at the difference between general and commercial aviation. While this may be obvious to many of us, there are some important distinctions which have a direct bearing on this work. The general aviation aircrafts or light aircrafts, such as the one shown in this first picture, compare with the commercial aircraft that most of us are used to flying on for business and holiday trips. Generally, commercial aircrafts are used for scheduled flights, say takeoff from large tarmacked airports, whereas light aircraft are most often used for leisure flights, sports flying, and of course training in the United Kingdom. I don't want to give you the impression that general aviation is purely a hobby. The government estimates that the economic impact of GA on the UK economy is around £3 billion of gross value added each year, and it supports around 38,000 jobs. So it is by no means an insignificant part of the economy. Further, there are discussions about GA aircraft taking on an increasingly commercial role in post-COVID world that we found ourselves in today. General aviation aircraft are characteristically much smaller than their commercial peers. They are commonly operated by a single pilot. They commonly have less sophisticated instrumentation, although this is changing, and many modern light aircraft have very sophisticated glass cockpits. They fly much lower, typically between 1 and 10,000 feet. They carry far few passengers, of course, and they are commonly not pressurized. The pilots are often, although not always, less experienced and less qualified than their commercial peers. Importantly for our discussion, it is the crews of General Aviation fleet which are most at risk from carbon monoxide poisoning, as we'll see a little later in this presentation. A talk on CO poisoning would not be complete without a slide on the symptoms. These are common symptoms that all pilots are taught about in their initial training. While cases of CO poisoning have the potential to be fatal in all environments, in general aviation, even levels of CO poisoning which do not directly induce unconsciousness or death are potentially fatal. Symptoms of CO poisoning such as headaches, fatigue, sleepiness, breathlessness are at best distractions to pilots, and there are well-known links between distractions of any type and aircraft incidents. Perhaps more of a concern are the effects of CO on cognitive functions. Carbon monoxide poisoning is known to result in impaired reasoning and decision making, something which is extremely dangerous to pilots. The Federal Aviation Administration, FAA in the US, carried out a study of a range of accidents between 1967 and 1993 and found that there was an estimated 360 victims which resulted from carbon monoxide poisoning. The result of the poisoning was in most cases not directly associated with death, not the direct cause of death. That would have been the loss of control of the aircraft or controlled flight into terrain. But rather, the root cause was impairment of the pilot's cognitive abilities, and this was believed to be the direct causal factor. Studies have shown that the main toxic effect of CO poisoning is tissue hypoxia. As you might expect, these symptoms are more pronounced at altitudes. Unsurprisingly then, in general aviation, the majority of carbon monoxide cases occur at altitude, with a split of 10 and 90 between ground and altitude operations, respectively. Of course, not every CO poisoning incident in general aviation results in a fatality. Many pilots are able to land safely. Even if an incident turns into an accident, some plane crashes are certainly survivable, even in small aircraft. It is also worth noting that just like in this picture, there is a fair chance that any forced landing or emergency landing can occur in an unpopulated area, or the pilot has an opportunity to direct the aircraft to clear areas where it can land and avoid collateral damage. Of course, this very much depends on where you fly, and indeed at what stage of the flight you are in. Many general aviation airports are not in nice open country, and so at least for takeoff and landing, the two most dangerous phases of flight, the aircraft are flying over populated areas. This little video clip, for example, is from my last flight, the last flight I took. And it's a good example that there is not too many areas that are available for landing should something untoward happen. And of course, if pilot judgment is impaired, the pilot might not remember that there is a nice race course within gliding distance of this location. The layout of a typical light aircraft might look something like that shown in this slide. We have all the common features you'd expect from an aeroplane. We have two wings, we have a tail, we have a place for our pilots to sit, and probably a place for some passengers to sit, if 2 or 4 passengers to sit as well. Typically, there's no door or partition between where the pilots sit and the cabin, so if one person is exposed, then everybody is going to be exposed to carbon monoxide, and the air ventilation system is equivalent and common in the cabin space on most GA aircraft. A single engine piston aircraft like the one shown in this slide will generally have the propeller and the engine at the front, providing drawing fuel from the wings, mixing it with air, igniting it, and providing power for the prop and to drive the aircraft forward. As a consequence of the combustion process, waste gases are produced, and these need to be removed from the engine, otherwise they will choke combustion. Similarly, a petrol-powered car, the waste gases are taken away from the engine and ejected into the air via the exhaust system. So there is considerable analogies between a car and aircraft engine and exhaust system. While the majority of cars on the road are relatively new, there of course are some older ones. The average age of the light aircraft fleet is surprisingly quite high. My aircraft, for example, it was manufactured in 1975, and that would not be considered a particularly old General Aviation aircraft. While these aircraft are generally reliable, I suppose they must be, has been flying for 30 or 40 years, they do lack design considerations you might expect from more modern airframes. Parts of the exhaust system cannot be viewed and thus cannot be easily inspected. The materials of construction suffer from a wide range of known failure modes, and they have a significant number of joints throughout the associated systems, which are also prone to failure. The result of all this is that leaks can occur, and if they do, exhaust gases can fill the engine bay. That's the space between the cowling, the outside of the skin of the aircraft, and the engine. The impact on flight performance might not be detectable at all. You might have a small change in sound, but if you're in flight, it's unlikely in a basic general aviation aircraft that the pilot would be able to detect a relatively small leak. And especially in aircraft without suitable instrumentation, which is common in general aviation. As a second line of defense, gases would be kept in the engine compartment, which sits here on the front of the aircraft, by a firewall. That's this represented here. This isolates the engine compartment from the passengers, protecting them principally from fire, but it also acts as a barrier to carbon monoxide. However, any holes, such as a missing bolt, a screw, poorly sealed fittings, etc., and there are many things that have to pass through this firewall, can allow ingress of exhaust gases from the engine compartment into the cabin. If this is not enough of a recipe for trouble, just like older cars, many general aviation aircraft use heat from the engine to provide hot air for the cabin. Imagine you wake up for work on a winter's morning and find that the temperature has dropped to -10. I'm reasonably sure that the first thing you would do after starting up the car is turn on the heater. You might expect a similar response from a general aviation pilot. In the simplest systems, heat from the engine is also used to provide heat for the cabin and de-icing equipment or any de-icing equipment that might be fitted. In a slightly more sophisticated aircraft, the hot air from the engine may pass through a heat exchanger. A single engine aircraft heat exchanger generally consists of a muffler, which is a stainless steel shroud. Heat from the outside passes between the muffler and the shroud and absorbs heat from the hot gases and the exhaust system, and then enters the cabin to keep people warm. I hope that it is clear that if there is a leak in the exhaust system, it is more than possible that air from the exhaust gases containing carbon monoxide can enter into the cabin through the heating system, either that or the de-icing system. The key points here are the design of the exhaust and heating system varies across models and manufacturers, of course, as you'd expect. Nevertheless, there are common factors. the basic functions, the operating conditions, a large number of connections, and mature material technologies, which are all subject to various failure mechanisms. For example, there is some data reported in the United States that after 400 hours of flight time, a typical 50% of a typical exhaust system for a general aviation aircraft will have some form of failure, crack or corrosion spot are typical. However, there is no mandated requirement to replace exhaust systems after that particular duration of time. The design of systems we are discussing and the materials from which they are made are at least mature, not necessarily bad, they've been in existence for a long time, but they do not use latest knowledge, understanding and technologies. There are better engineering options available, but the aviation industry is conservative and relatively few changes in materials or design are made on these parts. It should be noted that these parts and the parts under discussion all have a finite life. That is, the exhaust will be changed several times during the life of an aircraft, just as you might expect the exhaust on your car to require changing after so many years. The exhaust muffler system needs to be inspected during scheduled maintenance and during a pilot's pre-flight inspection. However, it is often difficult to do this for the entire system, as much of it is occluded and within the engine bay area itself, which is difficult to access on many aircraft. Taking this information together presents an opportunity to make improvements, design changes, selecting alternative materials, and the use of sensors. While the lessons learned from the past incidents are commonly factored into newly designed aircraft, the design of the bulk of the general aviation fleet, that is, older aircraft, remains relatively static. However, many of the parts are replaceable, and it is theoretically possible to integrate design materials improvements into new parts. I suspect the main reason why it has not happened is it would require considerable coordination between aircraft owners, pilots, aircraft manufacturers, regulators, engineers, designers. This next section looks at what is being done to reduce risks and make additional commentary on the opportunities where we could do more to reduce risks of carbon monoxide induced fatalities in the general aviation sector. The UK private pilot's license and the students who are aiming to get one are required to pass ground examinations in 9 different subjects. It really is quite a significant challenge even to pass the ground portion of pilot training for even a private pilot. The most relevant examinations to this presentation is a human performance exam. And as you might expect, carbon monoxide poisoning is one part of a rather full syllabus. Teaching methods are variable across different ground schools, and as with many subjects that are assessed via paper-based examinations, at the end there is an element of learning for the examination or cramming. The National Transport and Safety Board in the United States reported information regarding the maintenance and inspection of 62 aircraft which were involved in carbon monoxide related accidents. In cases where maintenance is categorized as inadequate, in this slide, it indicates that the repair of the component was not carried out according to procedures. Inadequate inspection means that the inspection missed an already existing problem. Missed inspection refers to aircraft that did not receive the required inspection or maintenance. It shows that 21 out of 62 of the aircraft that were involved in these CO-related accidents received their scheduled maintenance and inspections. However, the available information reveals that inspections did not meet the required standards in some cases. One aircraft missed some inspections and there was no information regarding 40 other aeroplanes. It suggests relation between deficient maintenance inspection practices and CO leakages as a cause for a number of these deficiencies. Perhaps the lack of data itself is the most telling conclusion which can be drawn from this. Further research on the procedures for capturing information and in the UK and maintenance of database and access to records is something that should be given a high priority. An electronic system, a national electronic system, which allows data to be easily managed by pilots and maintenance personnel would be of real value to the sector. Another important point is that at least some of the faults that caused carbon monoxide to enter the cabin were present before the flight. Some could have been detected by enhanced inspections, but certainly not all. While annual and routine inspection of exhaust systems by aircraft mechanics can provide detection of current leaks and identification of potential failure issues, it is clear they cannot anticipate some of the issues which inevitably occur between inspection windows. It is extremely difficult to carry out thorough inspections of all components of the exhaust system in crowded engine compartments. Also, corrosion and erosion occurring inside the exhaust will be extremely difficult to see without totally dismantling the entire system or a complete borescope inspection. Some accident reports have revealed CO poisoning as the cause of air crash even immediately after inspection, which suggests the minimum requirements for maintenance and inspection and servicing of the exhaust system need to be properly reviewed. The FAA, in response to these issues, recommend a daily pre-flight inspection, which includes complete external visual inspection of the exhaust system. While it is routine for pilots to inspect the parts of the exhaust system and other parts of the aircraft that they can see prior to every flight, it is not possible on all aircraft to inspect the exhaust system. And on those that it is, a flashlight, a mirror, a pick, and other tools are often needed, and it is just not practical in many situations. In the UK, the Civil Aviation Authority, or the CAA, is responsible for regulation of both commercial and general aviation. The CAA produces a number of documents which mandate various aspects of maintenance and inspection. Rather than review these regulations, let's talk about the safety bulletin that EASA, which is the European equivalent of the CAA and was until recently responsible for regulations in the UK. They issued a report after a considerable time after the Emiliano Salazar crash. After the incident in the UK Accident Investigation Branch created this report, and they looked at data not just from the this crash, but all crashes from between 2000 to 2020, and the report indicated that there were 24 accidents reported in the UK, approximately one every year. The report provided a list of recommendations, which are paraphrased here. Aircraft owners and operators should ensure that heating, ventilation systems and exhaust and manifolds remain in good condition and working order, and are serviced according to the manufacturer's specifications. This is reasonable advice. All be doing this anyway. And also, the manufacturer's documentation was written before the aircraft was produced. And as we have discussed, many of these aircraft are, to say the least, mature. The question is, can't we do a little better than this today? Can't we improve on these recommendations rather than relying on 30, 40-year-old information? Scheduled maintenance tasks should be added to aircraft's maintenance program. And here they're talking about specific maintenance tasks linked to carbon monoxide poisoning. However, not all maintenance professionals in the UK have access to the needed equipment or the specialist knowledge to investigate potential CO-related issues. Of course, all of them will have some knowledge and some awareness, but it would be asking quite a lot for them to be specialists in understanding CO causes in the general aviation fleet. Couldn't we set up a government-run or government-supported test centre, something like an MOT centre, where owners could take their aircrafts and have their uh, risks of CO evaluated, receive some professional, impartial recommendations about work they could do to mitigate any existing risks and improve overall safety. We have some good regulations and we have some good recommendations, but much more can be done when it comes to identifying and addressing CO risks in the GA fleet. The CAA considers carbon monoxide detectors as the second line of defence after inspection and maintenance to protect pilots from carbon monoxide poisoning. The accident data suggests that in the UK, when aircrafts are equipped with carbon monoxide detectors, the pilot is more likely, significantly more likely, to be able to land safely and avoid fatalities. Safety Advisory 34 from the CAA states that the CAA will evaluate the performance of passive and active CO detectors and will use the results for future rulemaking. So if I understand correctly, this work is going on at the moment. EASA, and we still draw upon many EASA recommendations, regulations in the UK, recommend that pilots and operators of aircraft with internal combustion engines, combustion heaters, etc., install and equip carbon monoxide detectors. Despite the fact that the available evidence indicates that CO detectors are effective in preventing fatal CO-related incidents, this is still only a recommendation and not mandated. The common types of CO detector used are biomimetic, semiconductor, infrared, and electrochemical sensors. And our sensor technology has improved dramatically over the last few years. Based on findings from an FAA investigation, electrochemical sensors seem to be the most suitable for general aviation. Further, their findings from this recent FAA study indicate that detectors should be mounted on the instrument panel to facilitate integration into a pilot scan and to ensure detection as early as possible. The instrument panel in GA aircraft backs onto, at least single engine aircraft, backs onto the firewall, and so it's obviously a good location to install the detector. The results indicate that carbon monoxide above 50 parts per million, and some of the more recent detectors claim 25 parts per million. The CA limit is 50 parts per million by volume for any period exceeding 5 minutes. There are two basic types of CO detectors used in general aviation. This slide shows the first. It is a simple passive chemical or spot detector. The presence of carbon monoxide will result in the orange spot changing colour, getting darker in this case. Types of passive detectors rely on the pilot seeing the change, as there is no audible warning. If a pilot uses such a detector, he will need to add it to his scan, scan being the set or path which he uses to keep an eye on all the instrumentation in the aircraft. This is the cheapest method of detecting CO. Chemical spot detectors, they have a relatively low threshold, less than 100 ppm. But these detectors can be installed anywhere in the aircraft. There have been reports of false positives from maintenance chemicals that are used in the aircraft, but these are relatively rare. They also do not give actual indication of CO level. They have no audible alarm, so they don't alert the pilot. And the performance of the spot detector can degrade over time, so they do need to be replaced every so often. This type of detector do have the advantages. They are cheap and that they can be used in any aircraft, which eliminates a couple of the more vigorous arguments that are common reasons pilots cite for not upgrading aspects of their aircraft. The second type of detectors are electronic detectors. or active detectors. These can be broken down into three main types really. The first is a portable detector, which pilot can carry with them, particularly useful if the pilot is flying multiple aircraft. The next one is an instrument that it can be installed hardwired into the aircraft's instrument panel. And the final one, newer perhaps, is linked to an electronic flight bag. Electronic flight bag would be some device that stores all of the maps, all of the airport data, that displays speed, position, coordinates, altitude, and gives a lot of information about the flight that the pilot needs. These are becoming increasingly common. They can be either installed into the aircraft, a glass cockpit effectively, so replacing all the analog gauges with electronic devices, screens like this, or they can be on an iPad. This is the approach I use in my aircraft, which has older gauges. It has an electronic flight bag on my iPad, which provides me with a lot of very useful information. This particular one, which I haven't got, I've got an earlier model of this, but this particular one, as well as providing GPS coordinates, altitude, weather, information about traffic, other aircraft, where they are and what altitude they're flying, and things like that. This newer version also has an integrated carbon monoxide sensor, which, of course, very valuable, equivalent to this, a portable sensor. It can log and record CO levels in the aircraft. It can alert the pilot because the electronic flight bag is linked to the pilot's headset, so we get audible alerts about location of terrain, location of aircraft, weather, and things like that. You can also get alerts about carbon monoxide level in the aircraft. So are very useful, and these are becoming more and more popular. Just want to finish with a notes on areas for future research or future work. Even relatively simple general aviation aircraft have built-in redundancies. When compared to modern training, regulation and the experience within the community, there is considerable safeguards in place to protect pilots from carbon monoxide poisoning. In fact, most of the aircraft in common use have such long service lives. It is testament to the robustness of the design and the systems that are in place. However, weaknesses in every system occur, and should these align with each other, that is when we end up with a carbon monoxide related incident. Identifying these holes and developing mitigation to block some of them is a reasonable strategy for risk mitigation in any sector, and it goes some way to strengthening or mitigating the risks of carbon monoxide poisoning. And it's been the focus of this work. I've talked about quite a few pieces of future work, and I'll summarize a few in this slide as well. There are of course more that we've covered earlier, and there are additional ones in the report. So we might want to consider as a priority carbon monoxide detectors. These need to be rigorously evaluated. Clear and consistent advice needs to be issued about what is suitable and what isn't suitable. And once that is done, their use needs to be mandated across the GA fleets. Inspection and maintenance are very useful and very powerful, but they are not totally effective against carbon monoxide poisoning. Evidence suggests that it is extremely difficult to carry out inspections of all components of the exhaust system in a crowded engine compartment. Pressure tests can help, as can other more advanced tests, but corrosion and erosion inside an exhaust system is difficult to detect. New approaches borrowed from other industries should be considered, along with a national testing program which offers low-cost, safety inspections with a focus on carbon monoxide leak detection and prevention. The design and materials used for some of the critical components is at best dated. Significant improvements in associated technologies exist, and these systems are replaced periodically, so an upgrading program for the fleet is certainly possible. It would, however, require significant technical investment, along with involvement of a wide range of stakeholders and a lot of coordination. The lack of data on aircraft incidents, on aircraft maintenance, on aircraft inspection, on aircraft use, on pilot performance and actions and flight history, especially when it comes to older aircraft, is a real problem. The lack of data prevents and limits understanding of the issues, which in turn limits what we can do about them. A national electronic system designed to support pilots and maintenance personnel may allow for improved data collection, increase the value of the fleet, and support future investigations. So this slide lists a few potential improvements and further work which could be done to further mitigate risks of CO poisoning. And I'd invite you to read the white paper to learn more. So thank you very much for your time in listening to me today. I would like to thank the CO Research Trust again for funding this work and the other tremendous work that they do. I've included A.G. McConnell's email address in this slide from the CO Research Trust, and I have no doubt he'll be able to assist you with any inquiries. I've also included my email address should anybody wish to get in touch with me in the future. Thank you very much again, and I hope to see you in person at the next event.